Okay, this is going to be a lecture that's going to go over the ideas of clustering and mixture models, Bayesian mixture models to do that. I'm not gonna get into the full details of the code in this clustering. I'm gonna aim to speak about the results and kind of speak informally about how the model works. And then I hope to follow up with an optional lecture where I'll dig into the code a little bit more. Okay, so clustering is in fact, clustering is unsupervised learning. So the idea of the way I would describe supervised versus unsupervised is supervised means you've got labels or you've got some labeled data to learn from, and unsupervised learning, you have no labels going in. So clustering is a type of unsupervised learning. And the idea, as it says here, is to group together groups of similar observations. So if you think back to our cartoon before where I had all of the blue data points and I ended up drawing 4 different bumps to describe those data points, we went from unlabeled data, they were all blue, to being clustered into different groups by the mixture model. So that's the aim of what we're going to do here. So it's similar in flavor to the density estimation model. It's easiest to think about clustering with multivariate data. So the density estimation problem that we looked at, we had univariate data, and so we were just building a one-dimensional density. Here, we're going to have multivariate data, and specifically we'll look at two-dimensional data because that's easy to picture, but this can be done in much higher dimensions. So we're going to start with multi-dimensional data, and the idea, as hopefully you have in mind, is we want to partition the data set into groups of observations with like observations. Okay, so the DMM for clustering. First of all, what is DMM? DMM is simply the Dirichlet mixture model. So this should be familiar from the first couple of lectures. We talked about Dirichlet mixtures. What we're going to have to do is we're going to have to assume some distribution. We will assume multivariate normal in the example, although again, that's not required for the model. We're going to start with K clusters, and K is going to be large, and what we're hoping is that the model will naturally reduce the number of clusters down to a sensible number. So even though K might be large, in our example, K is going to be 50. What we're going to do is we're going to see that the data ends up, after our model runs, being lumped into just 3 clusters. So behind the scenes, those other 47 clusters haven't gone away. They just don't have any data associated with them. Let's see. So this is our quantity of interest are the cluster assignments. So this is different than estimating the density. What we want to say is this group of data is cluster 1, this group of data is cluster 2. And as you'll see, there's a little bit of challenge to assigning a data point to a cluster because as our MCMC runs, a data point can move from one cluster to another cluster. Okay, we will need to learn a new distribution. The new distribution that we are going to learn is the Wishart distribution. And this is going to be essentially a multivariate analog to our gamma or our inverse gamma distribution. So when we were studying when we had a normal distribution, when we put a prior on sigma squared, we used the inverse gamma. Or if we wanted to put a prior on sigma to the -2, we used a gamma distribution. The Wishart distribution is going to be our prior distribution on our covariance matrix. So it's kind of crazy to think about, maybe at first, but imagine you've got a covariance matrix sigma, which is sigma 1, 1, sigma 1, 2, sigma, I'm going to say this is sigma 1, 2, sigma 2, 2. You might be saying, hey, Cooley, you got this wrong because that should be sigma 2, 1. But those, of course, the off-diagonal elements have to be equal because our covariance matrix is symmetric, so I'm going to label it that way. We can think of these sigmas as being random, and in fact, as good Bayesians, we are comfortable saying these sigmas are random. And yet they can't be anything. We've already talked about how sigma 1, whoops, I didn't mean to do that, sorry. The off-diagonal elements have to be equal so that this is symmetric, but there are other requirements on a covariance matrix. A covariance matrix, for instance, has to additionally be positive definite. And so our prior distribution, we want to reflect the restrictions on the values that a covariance matrix can take on. And so without going too deep into it, a Wishart distribution is a distribution over almost covariance matrices. In fact, the Wishart distribution is going to be a distribution over precision matrices. And you'll remember, I think maybe we've said this before, but if not, if we talk about a covariance matrix sigma, if I take its inverse, which sometimes gets called Q, the inverse of a covariance matrix is called the precision matrix. So our Wishart distribution is a distribution over the precision matrix. And so this is, as this bullet says here, this is analogous to putting a gamma distribution on sigma to the -2 in the one-dimensional case. So we could do a inverse gamma on sigma squared, we could do a gamma on sigma to the -2. This is essentially a one-dimensional precision matrix. So what are the takeaway messages? A Wishart distribution is a sensible distribution for precision matrices. It guarantees that the matrix is going to be positive definite, and it is nicely conjugate in our, really it's what I should be underlining is up here. It is the conjugate prior for the precision matrix of a multivariate normal. So it's conjugate, it's nice. Okay, so here a Wishart distribution has two parameters. This eta parameter has to be greater than p minus 1. And then this lambda matrix, it's actually a matrix, and it's p by p. So the probability density function of the Wishart distribution is given by this expression here, and that looks like a whole lot, but don't panic. This is just a PDF. And so the way a PDF works is it has some parameters that are fixed, and then it's a function of the matrix of the the argument that you put in, which in this case would be a matrix. So if you fixed eta and you fixed lambda, you could plug in different sigmas in here, or sigma inverses in here, and it would give you different values. And the higher value, the more the sigma that you plug in agrees with the parameters that you you defined your PDF with. Or better, a better term would be the more likely. This really would be okay. If you're curious about the TR, those are just the trace. So these are both matrices. We can multiply them together. We get another matrix. We can look at the diagonal elements of that matrix. If we sum the diagonal elements, that gives us the trace. This gamma sub p is a gamma function. I know there are a lot of things called gamma in this class, but the gamma function is like the function that appears in the normalizing constant of the beta distribution. Gamma p is a multivariate version of that. Okay, so we can describe properties of the Wishart distribution. If sigma is distributed Wishart eta delta, not delta, lambda, then the expected value of sigma inverse is eta times lambda, and the variance of sigma inverse is given by this expression. This is breaking it down into the ith and jth element of sorry, this gets just a tiny bit complicated. If we think of sigma being a matrix, so let's just assume it's 2 by 2. Each of these guys is random. Each of the 4 elements is random, and so I can talk about the variance of each of those guys and the variance of each component of sigma. So that's what we're talking about here. Over here is given by this expression. Okay, so it's got a mean. This is a matrix, tells you where it's centered. We can talk about the individual variances. Okay, so as a previous slide said, the Wishart is conjugate if we have a multivariate normal sampling distribution. And so this would be this is our a multivariate normal hierarchical model. So this is just saying our data, given the value of sigma, is distributed normal mu sigma. Down here are our priors. The prior on mu should look familiar. We've put normal priors on mu before. The prior on sigma inverse is our Wishart prior. And so you might be asking yourself, what we put on priors like sigma squared I, or pretty simple priors when we were talking about this before, but this Wishart in some senses allows us more flexibility than prior models that we have earlier models that we have looked at in this course. And it's conjugate, and so you can work it out. This is the posterior of the precision matrix given mu and x, and because it's conjugate, we know that it's Wishart. We started with a Wishart prior, we combine it with a multivariate normal, we get a Wishart posterior. Here is our posterior for mu given sigma inverse and x, and it's normal. So not surprising, we knew that if I put a normal prior on mu, I would get a normal posterior. And this just talks about the posterior in terms of the current value of sigma inverse. Okay, so that's all sort of prologue. What we want to do is we want to talk about our Dirichlet mixture model. And so the Dirichlet mixture model looks a lot like our mixture model for density estimation. We have each of our data points given the knowledge that Zi is in K. So what we're saying is, if I knew that data point Xi were in cluster K, then I would know that it has a normal distribution with mean mu K and with variance, covariance matrix sigma K. And the now you might pause and say, hey, wait a second. I mean, this is unstructured learning. I don't know which cluster it's in. And that's absolutely right. But as we move through our MCMC, what's going to be happening is each data point is going to be associated with a cluster at each step in our MCMC. And so this is just saying that in our current step of the MCMC, get the cluster assignment, and then you know the distribution of X. Here is our categorical from before. So this just says, given a vector of pi's, a vector of probabilities of being in each category, this allows you to draw from that vector of probabilities. We had a Dirichlet prior on the probabilities. Here is that Wishart prior. And so what the Wishart prior is going to do is it's going to allow this sigma to change and to basically be learned from the data. Then here is our normal prior on our mean. Okay, so what I want to do is show you the the basics of this model and how it works. So we're going to have 500 observations, and the true number of clusters is going to be 3. And what this code will do, if you look at it for a second, is it will simulate data arising from 3 clusters. And the data, it ends up looking like this. So here in this example, the clusters are really distinct, and they should be relatively easy to be learned. Okay? The code for this will be posted on Canvas, but it's going to be this dmmfunc.r, which in the next optional video, I will go through that code just a little bit. But what it's going to do is it's going to take the data that we generated X, it's going to run it for 250 steps, and we're going to see the clusters that come out. So I think the best picture for understanding how this works is this picture here. So what we have is, this is step 1 and then step 51. So what we're doing is we're seeing how the clusters evolve over time. Okay? Now, notice that the first step looks to be a real mess. Even though these clusters are well defined, our cluster assignments, which are shown by the colors on the right-hand side, there are a whole bunch of different colors. What's happened? Well, what this code does is it starts with these, let's see, we've got, we started with 500 points. So it starts with 500 points, and it just, because it doesn't know yet how to cluster things, it just assigns points to a random cluster. So in fact, what it does is K, the number of clusters, is going to be set at 50 for this example. Now you'll remember at the beginning of this lecture, I said you set K to be some number of clusters, and then it runs for a while, and a lot of those clusters end up being empty. So actually in every step there are 50 clusters, but some of these steps or some of the clusters end up without having any points. But when we begin, which is what is seen up here in the upper left, points are randomly assigned to 50 different clusters. And then the algorithm runs, and you can see that by the time we get to step 51, we're learning these different clusters pretty well. We've got a purple cluster down here. Notice that the purple cluster is somewhere in the 30s. Just looking over here at the assignments. So the numbers of the cluster don't matter all that much, but we got, a purple cluster. We have a green cluster that's, somewhere around 20. We've got a pink cluster somewhere down here. We've got a blue cluster. You see that blue cluster is kind of overlaying that pink cluster, but what could be happening at this step in the MCMC is that we've got right now the model thinks there are two different clusters there. There is a cluster with a covariance matrix. The pink cluster has a covariance matrix. Let me undo that. Let me try and draw that a little less. Here are maybe the ellipses that describe the covariance matrix associated with that pink cluster. And then this blue cluster would have a covariance matrix that leads to ellipses that are really narrow and skinny. But what you also see is that over time it likes adding that additional cluster less and less until by step around 200, what we have is we've got three pretty distinct clusters. Now, interestingly, notice that at step 250, we have this little blue cluster. So this nicely illustrates one of the things I said earlier, is that the points can change clusters over time. And what you're going to see is that the points, could, even once the chain is sort of in its happy state, clusters could get turned on and off. Now let me go back and just look at this output for just a second here. What this is saying is it's actually tracing the cluster number of an individual point, and that individual point was labeled 1. So what's going on here? When we simulated the clusters, we actually assigned the clusters to group 1 or group 2 or group 3. Notice what this is going to do is it's going to draw a random uniform. It's going to multiply it by 3, and then it's going to take the ceiling. And so every point gets a 1 or a 2 or a 3. And what this is doing is this is saying pick out a point that is labeled 1 and actually pick out the first point that had a label 1. And then it's saying which cluster, this is the cluster labels. Remember, our algorithm started off with 50 clusters. How many steps did it stay in that cluster? So it had 2 steps in the cluster labeled 2, 2 steps in the cluster labeled 3. It had 242 steps in the cluster labeled 21. So that's kind of where it ended up pretty quickly and seemed to be pretty happy there. We can do the same. This is just looking at another point that was originally in cluster 1. This is looking at the second point. You can see that it spent 4 time steps in cluster 3. It spent 7 time steps in cluster 4. And then it spent 239 steps in cluster 21. And not surprisingly, these 2 points ended up in the same cluster, which ends up being called cluster 21, because they were both in the same cluster in the generated data. You'll remember that the green cluster, we said one of these clusters was green, that's, corresponds with a number in the early 20s, and now we're seeing, this guy is that cluster 21, which all of the points from our original end up nicely in. And in fact, this plot shows that. This is just tracing this over the steps. What it's saying is which cluster, which of our 50 clusters do each of the points end up in. We're only looking at points which are originally labeled cluster 1. And you see that they move around a bit, but eventually all of them end up in that same cluster of 21. Now, this is a cartoon example because the clusters are really distinct. But if you look at this plot, this is actually arising from 5 clusters, but it's not really easy to see 5 distinct clusters, right? You're seeing some points that are bunched up here, you're seeing some points that are bunched up here, you're seeing some points kind of spread out in this direction, you're seeing points here, and we could colorize these points because we simulated them. We know that they arose from 5 different colors, so we could colorize the points, but that's sort of artificial. If you're actually doing a clustering problem, the data you start with looks like this. It's unlabeled, and so the notes also fit a Dirichlet mixture model to these clusters, and they do the same thing. What they're showing here is the evolution of a point that was originally in cluster 1. It likes being in what ends up being labeled cluster 28 by the algorithm. This other point also ends up there, but maybe it bounces back and forth a bit more between 28 and 21. And you can see that at the clusters, the points that were originally in cluster 1, because that's what this is tracing, they don't all end up in the same cluster. So what is this again shows the evolution, and you can see that it kind of settles in. Again, it starts off with random clusters assigned. It eventually seems to settle in where we've got some, kind of a green cluster here, a brown cluster here, a teal cluster there. But what's happening you're seeing some of the points change cluster assignments, and that's just going to continue to happen over the course of the MCMC. So what can you do about it? Well, one thing you could do is you could probabilistically assign points to the clusters. You could just, after you find the MCMC has settled into its steady state, you could see what proportion of time this point is a brown point and what proportion of time this point is a green point. Or if you want non-probabilistic cluster assignments, you could, it can be a little bit challenging. I think it would seem reasonable to assess or to assign to the cluster in which it spends its largest amount of time. And maybe that's what's going on behind the scenes with this Salso library. These are the true labels over here. This is assigning the best cluster. And it's trying to assign clusters as best it can, but the point switching, the label switching that we talked about at the beginning of this clustering lecture does make assigning a cluster challenging. All right, I'm going to stop there. That is a high-level overview of clustering via a Dirichlet mixture model.